Welcome to Lesson 27, Changing Higher Order Ordinary Differential Equations into Systems of First Order Ordinary Differential Equations. As an example, let's consider this second order homogeneous linear differential equation. Second derivative of x with respect to t plus 5 times the first derivative of x with respect to t plus 6x equals 0. Write it as a system of first order ordinary differential equations. So here's what we're going to do. We're going to introduce a function which we'll call z0 for x here. We'll introduce a function z sub 1 for dx dt here, and then this term is going to be z sub 1 prime of t. So, as I just said, we'll let z0 of t equal x of t. We'll let z1 of t be x prime of t up here. And then z1 prime of t is x double prime of t. We get this by just differentiating this equation up here. And so now we have x in terms of a z function, x prime in terms of a z function, and x double prime in terms of a z function. And the nice thing about this is the second derivative of x is just this first derivative of z1. So let's see what we can do with these new ways to express these functions x, and x double prime. So first of all, we can say that z1, which is x prime of t, is the derivative of z0, according to this equation. z1 equals z0 prime of t. The second thing we'll write down is an equation corresponding to what we have up here. The second derivative of x with respect to t is just z1 prime of t. 5 dx dt is just 5 times z1 of t. 6x is just 6 times z0 of t, and that equals 0. So that's what we have here. So this first equation came from what we had right here, and this second equation came from both of these and this differential equation up here. So now let's look at this for a minute. We usually wrote this before in terms of, let's say, z0 prime and z1 prime on the left, and then linear combinations of z1 and z0 on the right. So let's just do a little bit of algebra to rewrite it in that form. And we can do it pretty easily. Swap these two sides, and so we get z0 prime of t is equal to z1, which is the same as 0 z0 plus z1. And this next equation, just subtract these from both sides of this equation, and we have that z1 prime of t is minus 6 z0 of t minus 5 z sub 1 of t. Now, these can be written as a matrix equation. The vector z0 prime, z1 prime is the coefficient matrix 0, 1, minus 6, minus 5, that just comes from over here, times the column vector z0, z1. So we now have this in a form that we know how to solve. Let's consider this initial value problem. We have the same differential equation that we had in the previous example, and we're going to give initial conditions. X of 0 is 2, x prime of 0 equals minus 4. How could we write this in terms of a system of first order ordinary differential equations and take these initial conditions into account? Well, here's what we'll do, and let's go through it fairly quickly because it's almost the same as the previous problem. The only difference is now we have these initial conditions. So we'll still let z0 be x, we'll let z1 be x prime, and then z1 prime will be x double prime. And so we can write the differential equation plus the relation between z0 and z1 as this system of linear equations that we saw before, which we could rewrite this way. And we saw that this system of first order linear differential equations could be written in the form z prime equals a times z, so that doesn't change at all. The only thing that we have to add are two new conditions, the initial conditions, and we can write that in terms of a column vector. Remember that x is the same as z0 and x prime is the same as z1. So x of 0 equals 2 becomes z0 of 0 equals 2. X prime of 0 equals minus 4 becomes z1 of 0 equals minus 4. So not much new here, and we can solve this the way that we solved systems of equations earlier. So here is a second order problem, one that we've actually looked at before. A spring and mass problem. We have a wall, we have a spring attached to the wall, and we have a mass attached to that spring. So the mass will be 1 kilogram, and the spring constant will be 7/4 newtons per meter. And this system in here is surrounded by a fluid with a damping coefficient of 4 newtons per meter per second. At time t equals 0, the spring is stretched 1 meter from its equilibrium position with an initial speed of 2 meters per second towards the wall. That's in the negative direction if we set up our number line with 0 here and positive numbers going off to the right. Find x of t, the position of the end of the spring relative to the equilibrium position, 0. Assume there's no friction or gravity except for drag friction. So we've seen before that in this case we'll want to solve the second derivative of x with respect to t plus 4 dx dt plus 7/4 x equals 0. With initial conditions, x of 0 is 1, the initial position is 1, and x prime of 0 is minus 2. The initial velocity is minus 2. Remember that this equation up here is gotten by using this type of formula. The mass times the second derivative of x plus c times dx dt plus the spring constant times x equals 0. So with this initial value problem up here, let's change this first differential equation to a system first order differential equations. Let's let y1 equal x and y sub 2 equal x prime. In that case, as we saw before, we can write this as y1 prime equals y2 and y2 prime plus 4y2 plus 7/4 y1, which came from up here, equals 0. The initial conditions we can write as y1 of 0, y2 of 0, this column vector equals 1 minus 2. And then we can rewrite that as, well, first of all, rewrite these ordinary differential equations up here by getting y1 prime, y2 prime on the left-hand side of each equation. And where we need to, we'll put in two terms, like here we don't have a y1 term, so that's the same as 0y sub 1. And this one we can easily write this way. So then we can write it in this form, y prime equals a times y, and y1 of 0, y2 of 0, this vector equals 1 minus 2. And so here we have an initial value problem that we can solve for y1 and y2. Once we solve this for y sub 1 of t and y sub 2 of t, we will know from up here that y sub 1 of t is just x of t. So our solution for x is the same as the solution of this for y sub 1. So we're trying to solve this for y sub 1. We'll find y sub 2 along the way also, but our main interest is y sub 1. So here's the equation we're trying to solve, which we can think of as y prime equals a times y. A is this matrix up here. So first, let's find the characteristic equation for A, and then its eigenvalues, the eigenvalues of A. So the determinant of A minus lambda I is the determinant of this matrix. We subtracted lambda from each main diagonal entry. Set that determinant equal to 0. Evaluate this determinant, and it's 4 lambda plus lambda squared plus 7/4 equals 0. Don't like fractions too much if I can get away without them. So let's just multiply this equation, this characteristic equation, by 4 and rearrange the terms. If we do that, we can write it as 4 lambda squared plus 16 lambda plus 7 equals 0. Solve this quadratic equation for the eigenvalues. The eigenvalues are -1/2 and -7/2. Those are the solutions to this characteristic equation. Let's call this eigenvalue lambda 1. Let's call this eigenvalue lambda 2. So now that we have the eigenvalues, let's find the corresponding eigenvectors. So let's find the eigenvector for lambda 1 equals -1/2. So this is basically the matrix A minus lambda sub 1I times the vector v1, v2 equals 0, 0. Doing the arithmetic here, this is 1/2. This quantity down here turns out to be -7/2, and the secondary diagonal elements are not changed. So we have to solve this matrix times v1, v2 equals 0, 0 to find the eigenvector, which I'll call v1, v2 here. So let's look at this system of equations right here, given by this matrix equation. And let's use the augmented matrix for this system of equations and find the reduced row echelon form of it. So when we reduce this augmented matrix into reduced row echelon form, it turns out to be 1, 2, 0, 0, 0, 0. So v1 is the leading variable, v2 is the free variable. So let's let the free variable v2 equal t, and then solve this equation. v1 plus 2t equals 0. So v1 equals -2t. So that tells us that v1, v2, this vector, has to be t times -2, 1. So if we let t equal 1 here, an eigenvector corresponding to lambda 1, which was the eigenvalue, remember, -1/2, is this, -2, 1. 1 times this is -2, 1. I used p here, p1 actually, because later this is going to be the first column of a matrix P. So similarly, let's find the eigenvector corresponding to the eigenvalue -7/2. So we're going to look at the matrix A minus lambda sub 2 times the identity matrix I times the vector v1, v2, we'll just use this for the eigenvector, equals 0. Okay, when we do these subtractions of minus 7/2 from the primary diagonal elements, this is the matrix that we get. Now, let's augment this coefficient matrix with another column 0, 0 here, and solve this system by computing the reduced row echelon form of this matrix. It turns out the reduced row echelon form is 1, 2/7, 0, 0, 0, 0. So v1 is a leading variable, v2 is a free variable. So let's let v sub 2 equal t. Then this first row corresponds to the equation 1 times v sub 1 plus 2/7 times v sub 2, which is t, equals 0. Solve this, and we have that v1 and v2 are minus 2/7 t and t. We can factor the t outside of that vector. If we let t be 7, then we can get an eigenvector corresponding to lambda 2 to be p2, which is minus 2, 7. 7 times this entry is minus 2. 7 times 1 is 7. A multiple, a non-zero multiple of an eigenvector is still an eigenvector corresponding to the same eigenvalue. This way we got rid of some fractions. So if we let P be the matrix with columns being the two eigenvectors of A that we found, one eigenvector was minus 2, 1, the other eigenvector written as a column vector is minus 2, 7, and these corresponded to the eigenvalues minus 1/2 and minus 7/2. So if we compute P inverse AP, which will be, let's call it D, it'll be this diagonal matrix with the eigenvalues on the main diagonal. So at this stage, we know that the solution y1, y2 to our system is an arbitrary constant times the eigenvector corresponding to eigenvalue minus 1/2 times e to the minus 1/2 t. Then the second term, another arbitrary constant, times this eigenvector corresponding to eigenvalue minus 7/2 times the factor e to the minus 7/2 t. So this is the general solution to the ordinary system of ordinary differential equations. This is not the solution to the initial value problem, however. We still need to find out what C1 and C2 will be to satisfy the initial conditions. So let's look at the initial conditions. We were given that y sub 1 of 0 is 1, y sub 2 of 0 is minus 2. So let's put those in vectors. Y sub 1 of 0, according to what we have up here, if we plug in zeros for the t's, notice what happens. We'll have e to the 0, which is 1 here, a factor of 1 for this exponential, also here, and also here. So when we plug in a 0 for t into this thing, we just get minus 2c1 minus 2c2 for the first component of this column vector. 2c2 makes me want to square dance. And the second component is 7,1 plus 7c2. So this column vector equals this. That's equivalent to a system of two equations and the two unknowns, c1 and c2. Solving those by whatever method you want, we find out that c1 and c2 are both equal to minus a fourth. So plugging that back into our formula for y sub 1 of t, y sub 2 of t, what we have then is that this equals minus a fourth, looking at this formula right here, minus a fourth times that exponential times this vector plus minus a fourth times this exponential times this vector, and combining this column vector and this column vector into a column vector here by just adding the first components all the way through to get this first component. Similarly with the second components, we get that y1, y2 is equal to this and this. So remember that x of t was equal to y1 of t. Our original equation that we started with, the second order differential equation, was in the function x of t. And our substitution let y sub 1 be x. So x of t then is 1/2 e to the minus t plus 1/2 e to the minus 7/2 t. This last equation is practically the same, just eliminated this middle equation, I guess you can say. So anyhow, we have found the solution to the original initial value problem, which was a second order linear homogeneous differential equation with two initial conditions. The initial conditions on x of 0 and x prime of 0. So far we have y1, y2 equals c1 e to the minus half t times this vector plus c2 e to the minus 7/2 t times this vector. If we combine these two vectors, these two column vectors together, we get this column vector. The first topmost element is minus 2 e to the minus half t c1 minus 2 e to the minus half t times c2. Where did this come from? Well, we had c1 e to the minus half t times minus 2, which is right here, plus c2 e to the minus 7/2 t times minus 2, which is right here. Similarly, this exponential times 1 plus this exponential times 7 gives us the stuff down here. And so we have y1, y2, this stuff here, equals this vector, this column vector. And so, interesting, why did we do that? Well, if we look at this, we can imagine it as a product of a matrix times a column vector in a slightly different way than we had before. This column vector we can write as the 2 by 2 matrix right here times c1, c2. The way to think of that basically is maybe if you thought of having simultaneous equations in c1 and c2, what we have here is the coefficient matrix for a system of equations involving this times the variables c1 and c2, which in our case are actually arbitrary constants. Okay, so if you think about it for a minute, y1 is going to be this row times this column. So it's going to be c1 times this plus c2 times this, which is what we have up here. And similarly for the second entry. So we can think of this then as this column vector y of t equals this 2 by 2 matrix, which I'll call capital Y of t, times this column vector c1, c2. For any choices of constants c1 and c2, this equation will result in a solution to y prime of t equals a times y of t. So in a way, this matrix capital Y of t is fundamental, because by this equation we have all of the solutions to that system of linear homogeneous first order differential equations. This matrix y of t here is called a fundamental matrix for the system of ordinary differential equations. There's another matrix which often is called the fundamental matrix, which has a similar property, but we're not going to talk about that right now. Okay, so we have found solutions to our system of first order equations, but remember that we started with an initial value problem. And in addition to y1 and y2 satisfying two differential equations, they also had to satisfy the conditions that y sub 1 of 0 was equal to x of 0, and x of 0 had to be 1. y2 of 0 had to be x prime of 0, and x prime of 0 was equal to minus 2. So we need to find constant c1 and c2 in this formula right here and here that satisfy this also. So we're not quite through. We have to find c1 and c2 so that we have a solution to that initial value problem. So this was our general solution of y prime equals a times y. And we had initial conditions, y1 of 0 equals 1, y2 of 0 has to equal minus 2. So let's plug t equals 0 into this equation and see what happens. If I plug in 0 for t here, we get y1 of 0, y2 of 0. Over here, what does this matrix become? Well, e to the 0 equals 1. So here we have minus 2 times 1, minus 2 times 1, 1 times 1, 7 times 1. So at t equals 0, this matrix becomes minus 2, 1, and 7. C1, C2 are just C1 and C2. Now let's remember that y1 of 0, y2 of 0 has to equal 1 minus 2 by these initial conditions. So how can I solve this equation for C1 and C2? Just look at this part here. This matrix times C1, C2 equals this vector. How about we multiply this equation right here on both sides by the inverse of this matrix? So if we do that, C1, C2 is going to be the inverse of that matrix times 1 minus a half. Okay? Multiply this side by P inverse, multiply this side by P inverse. When you multiply these two out, you'll get minus a fourth, minus a fourth. Okay? And so that tells us then what C1 and C2 have to be, minus a fourth and minus a fourth. So now we can go back here and we can get our formula for y1 of t and y sub 2 of t now that we know what c1 and c2 are. So y1 of t, y2 of t, the solution to the initial value problem in this case, is that fundamental matrix times c1, c2, which turned out to be minus 1/4, minus 1/4. When you multiply this matrix times this column vector, this is what you end up with. Therefore, y1, y2, the solution to the initial value problem is this column vector. So y1 equals 1/2 e to the minus t plus 1/2 e to the minus 7t. Y sub 2 equals minus 1/4 e to the minus half t minus 7/4 e to the minus 7/2 t. We have solved the initial value problem y prime equals a times y with the initial conditions. Here's how we can use the Sage Math function DE_solve underline system to solve this initial value problem. first, in SageMath, we'll declare t to be a variable and outputs that it's t here. We'll define y1 to be a function of t. We will define y2 to be a function of t. The first ordinary differential equation we have is the derivative of y1 with respect to t equals y2 of t. The second ordinary differential equation is the derivative of y2 with respect to t equals minus 7/4 times y1 minus 4 times y2 of t. Notice in these equations we're assigning this stuff to OD1, we're assigning this stuff to OD2, and so we're using a single equal sign here. In the differential equation itself, when we want to say that this in the differential equation equals this in the differential equation, we use a double equal sign here. Similarly in this line. The next thing we'll do is solve that system. Solve the system, and then parentheses, and then in square brackets the list ODE1 and ODE2, which are the differential equations. We're solving them for y1 and y2, and the initial conditions are the following. At 0, y1 of 0 equals 1, y2 of 0 equals minus 2. When we execute these statements, this is the output of this last command. y1 of t is equal to minus a half e raised to the minus half t plus a half e raised to the minus 7/2 t. y2 of t equals minus 1/4 times e to the minus 1/2 t minus 7/4 e raised to the minus 7/2 t. If you remember, these are the solutions that we got by hand. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.